All right, you crazy kids. Dalton's law of partial pressures, Graham's law of effusion, and volumetric stoichiometry today. Let's start off with Dalton's. The total pressure in a system is equal to the sum of the partial pressures in that system. So, your total pressure is equal to all of the partial pressures, and so on. Meaning, if I have a balloon, woo, and there's some argon, neon, and oxygen in there, and I know argon is 1 atmosphere, neon is 2 atmospheres, and oxygen is 3 atmospheres, I can solve for the total pressure in that system. I simply add them together. All right, so the partial pressure of your argon plus the partial pressure of your neon plus the partial pressure of your oxygen would be 1 atmosphere plus 2 atmospheres plus 3 atmospheres will give you your total pressure, which is equal to 6 atmospheres of pressure. Kind of crazy. All right, Graham's law of effusion. The rate of effusion is inversely proportional to the square root of a gas's molar mass. So the rate is equal to 1 over the square root of a gas's molar mass. And when we're dealing with molar masses, we do the little capital M with a feet on it. What we're going to mainly do is compare the rate of one gas to the rate of another gas. And we're going to show you a calculation shown right here on how that actually looks. What this all comes down to is that lighter gases effuse faster and heavier gases effuse slower. Kind of just makes sense. A lighter gas, your molecules are generally going to be smaller and they have an easier time moving through the system. Heavier gas, molecules generally bigger, and they have a more difficult time moving through the system. That's why it takes a different amount of time depending upon the molar mass of the gas. In your packet, you're going to see rate 1 over rate 2 is equal to the square root of molar mass 2 over molar mass 1. That's how that looks. Let's try it out. So what is the molar mass of a gas that diffuses? That should probably read effuses 3 times faster than oxygen. What are we going to do to solve this? All right, so first of all, we need to actually, plug it into our formula. A rate is any distance over time. So I'm going to have 2 gases here. I'm going to have gas A and gas B. Gas A, I don't know. I'm going to make it X. All right, so I need something that's 3 times faster than gas B. So its rate might be 3 meters per second. Gas B, I know its identity. It's oxygen, O2, 32 grams per mole. And its rate would have to be then 1 meter per second. So gas A happens to be 3 times faster effusing. Let's plug this into our actual calculation. So we're going to have 3 meters per second over 1 meter per second is equal to the square root of 3200 over X grams per mole. And we're solving for X. When you're doing this, you guys have done this before, but I'll do it anyway. I'm going to have to square both sides, all right? And I'd have 3 squared is equal to 32.00 over x. Multiply both sides by x, so I get 9x is equal to 32.00. Divide by 9, I get, well, I've run out of space. Maybe we'll move this up a little bit. I get x is equal to 3.55 grams per mole. All right, I'm going to require you guys to show me your work on how you solve for this. You probably don't have to show me this stuff in purple, but you're definitely going to have to show me what's in green. All right, green is your actual formula here. You're going to have to show me your final answer, your unit, all that stuff. It's just how it works. When you're doing these calculations, I highly recommend you make gas A the faster of the 2 gases. It makes your calculation just a lot easier to deal with because you're going to end up with something over 1 and you know how many times faster it is than the other thing. So that's my, opinion on it. You can take it or leave it, but that's what I would recommend. Always make the fast gas A. All right, we got one thing left, and that's volumetric stoichiometry. So we have this question proposed to you. How many liters of hydrogen gas at 35 degrees Celsius and 0.98 atmospheres? Ooh, I'm just going to go ahead and add 273 to this right away because I don't want to deal with it later. 308 Kelvin. I needed to react completely with 875 grams of tungsten 6 oxide. And I gave the tungsten 6 oxide molar mass to you because I'm a nice guy. Here we see our formula, and it all looks gravy. This shouldn't be that big of a deal. However, it's now saying liters, and I get a temperature and a pressure. When you did stoichiometry before, you always solved for like moles or grams. Now, we need to solve for liters. What we're going to be doing is a stoichiometry problem followed by an ideal gas law problem. So I need to first find out how many moles of hydrogen gas are produced, and then I can plug that into PV equals nRT and solve for volume, and that'll give me the volume of gas actually produced. I'm going to solve this one live for you, kind of show you how it works. So I'm going to have my 875 grams of tungsten 6 oxide, WO3. That's a terrible 3. I need to first convert that to moles. So to have my 231.84 grams WO3 per 1 mole of WO3. I now am converting my moles of WO3, that's a terrible line, to moles of hydrogen. And if we look at the reaction, it's a 3-to-1 ratio, and that's how that works out. When I multiply this through, I get 11.32246 moles of H2. I don't round here. Do not round. The reason is I now have to plug that in to PV equals nRT. That's the number of moles of gas, and since the question is actually asking for liters, I need to solve for my volume. So volume now is going to be nRT over P. So that's number of moles, that's my 11.32246, that's pretty good looking too, moles, times my value for R. Considering the pressures in atmospheres, I'm going to use the right R value. That's 0.0821 liters times atmospheres over moles times K. Times our temperature, which is going to be 308 Kelvin, divided by our pressure, and our pressure is 0.980 atmospheres. I want you guys to show your work because it's another way for you to check your work. If we look, moles cancels out, atmospheres cancels out, Kelvin cancels out, and we'll be left with liters, which is what the question actually asks for. So make sure the units work in your calculations. When we do this through, we're going to get an answer in liters. My answer comes out to 292.15 liters of hydrogen gas. And now we have to think about sig figs. Well, I have 3 sig figs here, 3 sig figs here. This changes to 3 sig figs. Looks like everything has 3 sig figs. I'm going to round my final answer to 3 sig figs. That's 292 liters of hydrogen gas. That is how you do that problem. Everything that's shown here is required, besides, actually solving for the variables. But why not just solve for the variable? Because it doesn't take that much more time, and you'll definitely get the right answer. That's it for today.